But after we've chosen our algorithm and trained our model,
Right.
how do we know if it's actually any good?
That's where model evaluation comes in.
Okay.
Chapter 5.3 introduces the concept of splitting the data
Okay.
into training, validation, and test sets.
Splitting the data. Why do we need to do that?
Remember how we talked about overfitting?
Yeah.
That tendency for models to become too focused on the training data?
Yeah.
Well, splitting the data helps us avoid that trap.
Okay.
We train the model on one part of the data
Okay.
and then test it on a separate part to
Copy
see
that.
how well it generalizes to new, unseen data.
Okay, so we have a training set for learning
Right.
and a test set for the final evaluation.
Exactly.
What's the validation set for?
The validation set is used to fine-tune the model
Okay.
and choose the best hyperparameters.
Okay.
It's like a dress rehearsal
Okay.
before the final performance on the test set.
I like that analogy.
Yeah.
So the training set is for learning.
Right.
The validation set is for fine-tuning.
Uh-huh.
And the test set is for the final evaluation.
Exactly.
But even with this splitting strategy,
Yeah.
we can still run into the problems of underfitting and overfitting.
Right. Of course.
Chapter 5.4 goes deeper into those issues.
Underfitting is when the model is too simple
Okay.
and fails to capture the underlying patterns in the data.
Okay.
While overfitting is when the model is too complex
Yeah.
and starts memorizing the training data
Right.
instead of learning the general patterns.
So it's like finding that Goldilocks zone again.
Exactly.
The model needs to be complex enough to learn,
Right.
but not so complex that it overfits.
And Chapter 5.5 introduces regularization techniques
Right.
as a way to combat overfitting.
Okay.
Methods like L1 and L2 regularization help prevent overfitting
Okay.
by adding a penalty
Okay.
to the complexity of the model.
So it's like adding a cost to having too many parameters in the model, encouraging it to be simpler
Yeah.
and more generalizable.
Right.
But once we've trained and regularized our model,
Right.
how do we actually assess its performance?
That's where performance metrics come in.
Okay.
Chapter 5.6 dives into the world of metrics like accuracy,
Okay.
precision, recall, and the F1 score,
Uh-huh.
as well as tools like the confusion matrix
Yeah.
and the ROC curve.
Okay, that's a lot of metrics. Can we break them down one by one?
Sure.
What's accuracy all about?
Accuracy is the simplest metric.
Okay.
It tells us the percentage of examples that were correctly classified.
Okay.
However, it can be misleading when dealing with imbalanced data sets,
Okay.
where one class is much more common than the other.
Imbalanced data sets, like our spam detection example,
Exactly.
where most emails are probably not spam.
That's where precision and recall come in.
Okay.
Precision measures how many of the examples that our model classified as positive
Okay.
are actually positive,
Okay.
while recall measures how many of the actual positive examples
Were correctly classified by the model.
So precision is about minimizing false positives,
Right.
and recall is about minimizing false negatives.
You got it.
Okay.
The F1 score combines precision and recall into a single metric,
Well,
giving us a balanced measure of performance.
what about that confusion matrix you mentioned?
Yeah, the confusion matrix is a handy table
Okay.
that shows us how many examples were correctly and incorrectly classified
Okay.
for each class.
Fine.
It gives us a visual breakdown of the model's performance
Okay.
and helps us identify where it's making mistakes.
So it's a more detailed way to understand
Right.
the model's strengths and weaknesses.
Exactly. And then we have the ROC curve,
Okay.
which is a graphical representation of the model's performance
Okay.
across different thresholds.
Thresholds. What are those?
Some models, like logistic regression, output probabilities.
Okay.
A threshold is a value that we set
Okay.
to determine which predictions are classified as positive.
And which are classified as negative.
So if the model predicts a probability of 0.8
Right.
and our threshold is 0.5, that prediction would be classified as positive.
Right. Okay.
The ROC curve shows us how the model's performance changes
Okay.
as we adjust that threshold,
Okay.
which can be helpful for finding the optimal balance
Okay.
between true positives and false positives.
This is all very insightful.
Good.
But what if we don't have enough data to create separate training validation
Right.
and test sets?
That's a common problem.
It is.
Chapter 5.7 introduces cross-validation
Okay.
as a technique for evaluating models.
Okay.
When our data set is limited,
Yeah.
the basic idea is to split the data into multiple folds,
Okay.
then train and evaluate the model multiple times
Okay.
using different folds for training and validation.
So it's like rotating the roles of the training and validation sets
Exactly.
to make the most of our limited data.
This helps us get a more robust estimate of the model's performance.
And avoid overfitting to a specific train test split.
This has been a fantastic deep dive into the fundamentals of machine learning.
It has been.
We've covered so much ground.
Yeah, we have.
From the basic concepts of supervised learning to practical considerations like feature engineering and model evaluation.
It's amazing how much information Burkov manages to pack into just a few chapters.
I know, right?
And we're just getting started.
Okay.
Chapter 6 takes us into the exciting world of neural networks and deep learning.
Neural networks. I've always been fascinated by them.
Yeah, they're cool.
Aren't they inspired by the human brain?
They are. Neural networks are essentially mathematical functions.
Okay.
Structured in a way that mimics the interconnected neurons in our brains.
Okay.
They consist of layers of interconnected units or neurons.
Units. Are we talking about biological cells here?
Not quite.
Okay.
Think of them as mathematical representations of neurons.
Okay.
Each unit takes inputs, performs a calculation, and produces an output, just like neurons in our brains transmit signals.
So it's like a mini processing center within the network.
How do these units connect to each other?
That's a great question.
The connections between units have weights, which determine the strength or importance of each connection.
Okay.
These weights are adjusted during training to optimize the network's performance.
It's like the strength of synapses in our brains.
Exactly.
Which determines how effectively signals are transmitted between neurons.
The book introduces a simple type of neural network called a multi-layer perceptron, or MLP, which is a feed-forward network.
Feed-forward, what does that mean?
It means that information flows in one direction through the network from the input layer to the output layer without any loops or feedback.
Okay, so no roundabouts or detours in a feed-forward network.
It's like a one-way street for information.
Okay, but before we go deeper into architectures, can you explain the role of activation functions in neural networks?
Activation functions are crucial for introducing nonlinearity into the network.
Okay.
Remember how linear models struggle with data that can't be separated by a straight line?
Yeah.
Well, activation functions give neural networks the flexibility to model complex, nonlinear relationships.
Ah, nonlinearity. Those curves and bends in the data that linear models can't handle.
Exactly.
So activation functions help neural networks capture those intricate patterns.
Can you give us some examples of activation functions?
Sure.
The book mentions popular ones like the sigmoid function, tan and ReLU. The sigmoid function squashes the output of a neuron to arrange between 0 and 1, which is useful for problems involving probabilities.
We encountered the sigmoid function earlier.
Yeah, we did.
In logistic regression.
What about tan and ReLU?
Yeah, what about those?
Tan is similar to sigmoid.
But squashes the output to a range between -1 and 1. And ReLU, or rectified linear unit, is a simpler function that outputs 0 for negative inputs and the input itself for positive inputs.
So they all introduce nonlinearity in different ways, giving neural networks the power to model a wider range of relationships in the data.
I thought we were talking about deep learning.
Oh, yeah.
What makes a neural network deep?
What does make it deep?
That's a great question.
Yeah.
Chapter 6.2 explains that deep learning is distinguished from traditional neural networks by the use of multiple hidden layers.
Hidden layers? What are they hiding from?
They're called hidden because they're not directly connected to the input or output layers. They lie between the input and output layers and allow the network to learn more complex, hierarchical representations of the data.
So the more hidden layers. The deeper the network and the more complex the patterns it can learn.
It's like adding more levels of abstraction.
Yeah, it's a good way to think about it.
To understand the data.
But training deep networks used to be a real challenge because of something called the vanishing gradient problem.
The vanishing gradient problem. That sounds ominous.
It kind of is.
What is that all about?
Imagine you're trying to send a signal from the bottom of a deep well to the surface. The signal might get weaker and weaker as it travels upwards, eventually vanishing before it reaches the top.
So the deeper the network,
the
harder it is to effectively transmit information and train the network.
That's the basic idea. But the book reassures us that modern deep learning algorithms have largely overcome these challenges.
Good.
Through the use of more robust activation functions like ReLU and clever architectures like LSTMs and residual neural networks with skip connections.
LSTMs and skip connections. Those sound intriguing.
They are.
Can you elaborate on how they help address the vanishing gradient problem.
So LSTMs,
Yeah.
or long short-term memory networks,
Oh, right.
have a sophisticated memory mechanism
Okay.
that allows them to selectively remember or forget information from previous steps.
Okay.
This helps them handle long-range dependencies in the data
Okay.
and mitigate the vanishing gradient problem.
So it's like they have a filter
Right.
that helps them decide what information is crucial to remember.
Exactly.
What can be safely forgotten.
What about those skip connections?
Yeah, what about those?
Skip connections in residual networks
Okay.
create shortcuts that allow information to bypass certain layers,
Okay.
making it easier for gradients to flow through the network during training.
It's like having express lanes on a highway to bypass traffic jams
Right.
and keep information flowing smoothly.
I'm eager to see how deep learning is applied in practice.
Me too.
What kind of real-world problems can these powerful networks tackle?
Yeah, what can they do?
Well, Chapter 6.3 introduces convolutional neural networks,
Okay.
or CNNs, which have revolutionized image processing.
CNNs. I've heard they're amazing at recognizing objects in images. They are. How do they work?
CNNs are designed to exploit the spatial structure of images.
Okay.
They use a technique called convolution, which involves sliding a filter over the image to extract features.
A filter. Like an Instagram filter that makes your photos look vintage.
Not quite.
Okay.
These filters are mathematical operations that detect specific patterns in the image, like edges, corners, or textures. It's like having a magnifying glass that helps the network focus on the important details.
So by training on lots of images, the network learns to create filters that can recognize specific objects.
Exactly. And they've achieved remarkable results in various applications. From image recognition and object detection to image generation and even medical image analysis.
That's incredible. But images are just one type of data.
Right.
What about sequences, like text or time series?
That's where recurrent neural networks, or RNNs, come in. Chapter 6.4 is all about these fascinating architectures.
RNNs. I've heard they're great at understanding natural language.
They are.
How do they handle sequential data?
RNNs have a special memory mechanism that allows them to process information from previous steps in the sequence. It's like they have a short-term memory that helps them understand the context of a sentence or a time series.
So it's like they can remember what they've read or seen before, which helps them make sense of the current information.
Exactly. The book explains how RNNs work by introducing the concept of a hidden state, which is updated at each time step based on the current input and the previous hidden state.
So it's like a running tally of what the network has learned so far from the sequence.
But you mentioned that traditional RNNs have limitations.
Yeah.
Especially with long sequences. What's the issue there?
What is the issue?
Traditional RNNs can suffer from the vanishing gradient problem.
Right.
Which we discussed earlier.
That vanishing gradient problem seemed to be a recurring challenge.
It is.
In deep learning.
As the sequence gets longer, the gradients can become very small, making it difficult to train the network effectively. But luckily, as with other architectures, there are solutions.
Good.
The book mentions that gated RNNs, like LSTMs, have largely overcome this problem, thanks to their more sophisticated memory mechanisms.
LSTMs to the rescue, once again.
Yeah.
They seem to be a real game changer in deep learning.
They are.
What are some real-world applications of RNNs and LSTMs?
They've achieved impressive results in natural language processing, speech recognition, machine translation, time series analysis, and many other applications that involve sequential data.
This is all fascinating.
It is.
But we've been focusing almost exclusively on supervised learning.
Right.
What about unsupervised learning?
Good point. It's time to explore that. What's happening in Chapter 9?
What is happening in Chapter 9?
You're right. It's time to explore the world of unsupervised learning. Where we don't have those helpful labels to guide the algorithms.
So no cheat sheet this time.
Right.
How do algorithms learn without labels?
Unsupervised learning is all about discovering patterns and structures in the data without explicit guidance. It's like exploring a new city without a map. You have to rely on your observations and intuition to figure things out.
That sounds challenging but exciting.
Yeah, it is.
What kind of problems can unsupervised learning solve?
One common task is clustering, which involves grouping similar examples together based on their inherent characteristics. The book introduces the k-means algorithm, a classic clustering algorithm that iteratively assigns examples to clusters based on their distance to the cluster centers.
So it's like grouping stars into constellations.
That's a great analogy.
Based on their proximity in the night sky.
But just like with K and N, choosing the right number of clusters, the K and K means can be tricky.
It can be, yeah.
How do we determine the optimal number of clusters?
Yeah, how do we do that?
There are various techniques.
Okay.
And the book mentions one called prediction strength,
okay,
which can help us estimate the best K for our data.
Yeah.
But clustering isn't the only task in unsupervised learning, right?
Right. What else can unsupervised learning do?
Another important task is dimensionality reduction, which is about reducing the number of features in the data while preserving the most important information.
Reducing the number of features. Why would we want to do that?
High-dimensional data can be computationally expensive and difficult to visualize and interpret. Dimensionality reduction simplifies the data and makes it more manageable while retaining the essential information.
It's like summarizing a long, detailed book into a shorter version while still capturing the main thing.
And one popular dimensionality reduction technique is principal component analysis, or PCA. PCA finds the directions of greatest variance in the data and projects the data onto those principal components, effectively reducing the number of dimensions while preserving as much information as possible.
Directions of greatest variance.
Yeah.
That sounds a bit abstract.
It does.
Can you give us a visual analogy?
Imagine you have a scatter plot of data points. PCA finds the lines that best capture the spread of the data, like the axis of an ellipse. That encloses most of the data points. By projecting the data onto these lines, we can represent the data in fewer dimensions.
While still capturing the most important variations.
That's a helpful visual. But are there other dimensionality reduction techniques besides PCA?
Absolutely. The book also mentions autoencoders, which are a type of neural network trained to reconstruct their input.
Reconstruct their input. Isn't that a bit redundant?
It might seem that way. This is all starting to feel very advanced.
It is.
But I'm curious to explore beyond supervised and unsupervised learning. What comes next in the book?
Chapter 7 takes us into the fascinating world of ensemble learning, where we combine multiple models to create a more powerful, accurate model.
Combine multiple models.
Yeah.
It's like having a team of experts working together to solve a problem.
Precisely.
Each bringing their unique strengths to the table.
The book introduces two powerful ensemble learning algorithms. Random forest. And gradient boosting.
Random forest. It sounds like something out of a fantasy novel.
It does, yeah.
What's so special about it?
Random forests are collections of decision trees. Each trained on a different random subset of the data and features. This randomness helps create diversity among the trees. Which leads to a more robust and accurate model when their predictions are combined.
So it's like having a forest of different perspectives, each contributing to the final decision.
Exactly.
What about gradient boosting? How does that work?
Gradient boosting is a more iterative approach. It starts with a simple model and then gradually adds more complex models, with each new model focusing on correcting the errors of the previous models.
So it's like building a house brick by brick.
That's a great analogy.
Each layer adding more stability and refinement.
Gradient boosting is known for its high accuracy and is widely used in machine learning competitions and real-world applications where accuracy is paramount.
These ensemble methods sound incredibly powerful.
They are, yeah.
What else does the book cover in terms of more advanced concepts?
Chapter 8 delves into semi-supervised learning, reinforcement learning, and one-shot learning.
Let's unpack those one by one.
Sure.
Starting with semi-supervised learning. I'm guessing it's somewhere between supervised and unsupervised learning.
You got it. Semi-supervised learning leverages both labeled and unlabeled data to train models. It's particularly useful when we have a small amount of labeled data, but a large amount of unlabeled data.
So it's like trying to learn a new language. By reading a textbook with some translations. And then immersing yourself in a foreign country. To further improve your understanding.
That's a great analogy. The algorithm can use the labeled data as a foundation and then refine its knowledge by exploring the unlabeled data.
What about reinforcement learning?
Reinforcement learning is inspired by how animals learn through trial and error. It involves an agent that interacts with an environment and receives rewards or penalties based on its actions.
So it's like training a dog with treats and scoldings.
Exactly.
The dog learns to maximize its treats by performing desired actions.
The agent learns to maximize its rewards over time by exploring different actions and observing the consequences.
What are some examples of where reinforcement learning is used?
Reinforcement learning has been successfully applied to game playing, robotics, control systems, and even personalized recommendations.
And what about one-shot learning? That sounds like a real challenge for machines.
One-shot learning is about teaching algorithms to learn from just one or a few examples, which is closer to how humans learn.
So instead of needing thousands of cat images to recognize a cat, the algorithm could learn from just a handful of examples.
Exactly.
That's pretty remarkable.
It is.
One-shot learning is still an active area of research.
Yeah.
But it has promising applications in areas like image recognition, natural language processing, and drug discovery.
It sounds like the future of machine learning is all about making algorithms more efficient and adaptable.
It really does.
But before we jump too far ahead, let's take a closer look at some real-world applications of machine learning. Chapter 10 is all about that.
Real-world applications. Now we're talking. I'm ready to see how all this theory translates into tangible solutions.
I think you'll find it interesting.
What are some of the exciting areas that the book covers?
It delves into areas like image recognition, natural language processing, recommender systems, anomaly detection, and even the potential impact of machine learning on different industries.
Recommender systems are those algorithms that suggest products or movies you might like.
Yes.
How do they work their magic?
The book explains how recommender systems work by introducing two main approaches, collaborative filtering and content-based filtering.
Collaborative filtering. I'm guessing that's about leveraging the preferences of similar users to make recommendations?
You got it. Collaborative filtering is based on the idea that people who have liked similar things in the past are likely to like similar things in the future.
So if I enjoy the same movies as you, then the algorithm might recommend movies that you've liked, but I haven't seen yet.
Exactly.
Okay.
And content-based filtering focuses on the features of the items themselves.
So if I tend to watch action movies, then the algorithm might recommend other action movies. Even if other users haven't necessarily liked them.
Exactly. And many recommender systems use a hybrid approach, combining both collaborative and content-based filtering to make even more personalized recommendations.
It's all about understanding your preferences and finding the best matches.
What about natural language processing? I'm fascinated by how machines are becoming better at understanding and generating human language.
It's amazing, right?
It is.
Yeah.
The book provides a brief overview of natural language processing, or NLP, highlighting key tasks like sentiment analysis, machine translation, and text summarization.
Sentiment analysis is about understanding the emotional tone of text, right? Like figuring out if a customer review is positive or negative.
And machine translation is about automatically translating text from one language to another.
Like Google Translate.
Exactly.
And text summarization is about condensing long pieces of text into shorter, more concise versions while preserving the key information.
You got it. NLP is a vast and rapidly evolving field.
It is.
With applications in chatbots, virtual assistants, search engines, and many other areas.
It's amazing to see how machine learning is transforming the way we interact with language and information.
Absolutely. And the book also touches upon image recognition. A field where deep learning has made incredible strides. We talked about CNNs earlier.
Yeah, we did.
But there's so much more to explore in this area.
Image recognition has applications everywhere, from self-driving cars to medical diagnosis.
Yeah, it's mind-blowing.
It really is.
It is. And then there's anomaly detection, which is all about identifying data points that are unusual or different from the norm.
Like those credit card fraud detection systems.
Exactly.
That alert you to suspicious transactions.
Anomaly detection has applications in cybersecurity, fraud prevention, system monitoring, and many other areas where identifying unusual events is crucial.
Wow, this is just a glimpse into the vast world of machine learning applications.
It is.
It's incredible to see how this technology is being used to solve real-world problems across various industries.
Yeah, absolutely. And the book emphasizes that this is just the tip of the iceberg.
Right.
As machine learning continues to evolve, we can expect even more innovative applications and breakthroughs in the future.
It's exciting to think about.
It is.
But before we conclude this deep dive,
Okay.
let's shift our focus back to the book itself.
Right.
What are some of the key takeaways?
Yeah, what did we learn
from the 100-page machine learning book? Well, one of the things that struck me was how Burkov manages to condense such a complex topic into such a concise and accessible format.
I agree.
He doesn't shy away from the technical details.
No, he doesn't.
But explains them in a way that's easy to understand.
Yeah.
Even for someone who's not a math whiz.
He uses really clear language, intuitive examples, and helpful visuals to demystify the core concepts of machine learning.
It's a really well-written book.
And he doesn't just focus on the theory. He also connects those concepts to real-world applications.
Yeah, he does a great job of that.
Making it clear why these techniques are so important and impactful.
I also appreciated the structure of the book.
Yeah, the structure is good.
He starts with the fundamentals.
Right.
Building a solid foundation before diving into more advanced topics.
Exactly.
This gradual progression makes the learning process more manageable and enjoyable.
And he strikes a great balance between breadth and depth.
He does.
He covers a wide range of topics, from basic algorithms to deep learning, while still providing enough detail to ensure that readers grasp the key concepts.
Yeah.
It's a great starting point for anyone wanting to gain a comprehensive understanding of machine learning.
This has been an incredible journey through the world of machine learning.
It has been.
We've covered so much ground.
We have.
From the mathematical foundations to real-world applications, and even a glimpse into the future of this rapidly evolving field.
It's exciting.
What are your final thoughts on this deep dive?
I'm amazed by how much we were able to unpack from just one book.
I know, it's incredible.
And I think it highlights the incredible power and potential of machine learning.
Yeah.
From personalized recommendations to self-driving cars and medical breakthroughs, this technology is already transforming our world in countless ways.
And as machine learning continues to evolve,
yeah,
we can expect even more groundbreaking innovations and advancements that will shape our future.
I agree.
But before we get carried away with visions of the future, let's take a moment to appreciate the book that guided us on this incredible journey.
Right.
What are your parting words about the 100-page machine learning book?
This book is a testament to the fact that complex topics can be made accessible and engaging.
I agree.
It's a fantastic resource for anyone wanting to gain a solid understanding of machine learning.
Yeah.
Without getting overwhelmed by technical jargon or excessive details.
For sure.
It provides a clear, concise, and insightful introduction to this transformative field.
I couldn't agree more. It's a must-read for anyone curious about machine learning.
Absolutely.
Whether you're a student, a professional, or simply someone who wants to understand the technology that's shaping our world.
And with that, we conclude our deep dive into Andriy Burkov's The 100-Page Machine Learning book. We hope you've enjoyed this journey as much as we have.
And as always, keep those brains buzzing and those algorithms churning.